Okay, the universal set here is a class of 30 students. We have 20 elements in this set here, 6 elements in the set for biology students. We're given that 4 study both physics and biology, so in the intersection we have 4 elements. So we usually look for the intersection first and then we work out from that. So with 20 in total here, so we must have that 16 students study physics only. Since 6 students in total study biology, 2 of them study biology only. Now in total we have 30 students. Notice here that from these 3 regions we have 22 students accounted for, which means that 8 students must study neither physics nor biology. Now imagine randomly selecting a student from this class of 30 students. So each of the 30 students is equally likely to be chosen as every other student. The event E is that student studies physics, and the event F is that randomly selected student studies biology. So for example, the probability that event E occurs means the probability that the student that is randomly selected from all 30 students comes from this set here. Well, each student is equally likely to be chosen, so to calculate that probability we just get the proportion of students that study physics. So that's 16 and 4 is 20 out of the total, which is 30. So that's 2/3. So event E has occurred if the randomly selected student was one of these 20 students. Similarly, the probability that event F occurs is the probability that the randomly selected student from the class of 30 comes from set F. Well, we have 6 elements in set F, 4 plus 2, and we want to get the number of elements in set F as a proportion of the total. So that's 1/5. Now we want to investigate if events E and F are independent. So to do that we need to calculate either the probability of E given F or probability of F given E. Let's look at the probability of E given F. So what does this mean? Well, it means that we want the probability that event E occurs given that event F has occurred. So we have to imagine that the student has been selected from set F already. So we want the probability that that student is also in set E. So basically we want the proportion of set F of students that belong to E. So we want to consider the number of elements in F. And we want to look at the number of elements that belong to E and F. So you see we're selecting from set F now because we're conditioning on the fact that F has occurred. So the student has been selected from set F. So the student has been selected from one of the student is one of the 6 elements of F, one of the 6 students of F. And what proportion of those students are also in E? Well, you can see that that's going to be 4/6, 4 out of 6. So 2/3 of the students that are in F are also in E. So notice that this answer is the same as the probability of E without any conditioning. Okay, we got 2/3 for probability that event E occurs. So that tells us that E does not depend on F. So whether or not F has occurred, we're going to get the same answer for the probability of E. We're going to get 2/3. E does not depend on F means of course that E and F are independent events. Let's suppose that we consider the probability that F occurs given that E has occurred. So given that we have selected a student from set E, so that's we need to consider the number of elements in E. Well, that's 20. So what proportion of them also belong to F? Well, you can see that we're interested in the number of elements in both E and F, and that's 4. This is 1/5. But this is just the same as the probability of F occurring without any conditioning. So whether or not event E has occurred makes no difference to the probability. The probability is still going to be 1/5. So we could have done the problem this way. So just as a reminder, let's look at this more carefully. Now let's go back to probability of E given F. So intuitively we know it's this quantity here, but imagine that we divide above and below by the number of elements in U, in the universal set. So we've done this before. This is just an aside, just a reminder. So we saw before that the number of elements in the subset of U, E intersecting F, divided by the total number of elements in U, is just the definition of the probability of that set, that event, E intersecting F here. Similarly, underneath here, this quantity is just the probability of F. So the event that we're conditioning on appears in the denominator. Now we've already seen that since E and F are independent events, the probability of E given F is just the probability of E. So the probability of E is equal to this thing. So that tells us that since if the events E and F are independent, then the probability of E intersecting F is probability of E multiplied by probability of F. So we could have used this here for proving that events E and F are independent. This is another way we could have done it. Okay, so let's just show that probability E intersecting F is the number of elements in the intersection, which is 4, over the number of elements in the universal set, which is 30. And if we multiply probability of E by probability of F, we get 2/3 by 1/5. Okay, that's 2 over 15. Which, and these are the same. 4 over 30 is also 2 over 15. So these are indeed equal. So that tells us that E and F are independent events. As an aside, we will show that if probability of E given F is probability of E, then probability of F given E is probability of F. Now we may have proven this before. Intuitively this makes sense. If probability of E given F is probability of E, then E and F are independent events. So the fact that F has occurred does not affect the probability of E occurring. So if E and F are independent, then F is independent of E also. So we would sort of expect this result intuitively, but let's use a formula to prove it. Okay, so I'm using the formula for probability E given F. So F is the event that's conditioned on, so it appears in the denominator. And in the numerator we have the intersection of the two sets. But of course, since E and F are independent, we can set this equal to probability of E. Okay, so we're just using this result here. That's what we're given. And by cross multiplying we get this result that we saw already. Now let's look at what we're trying to show. Let's look at probability of F given E. Well, we use our formula, so we need to get the probability of the intersection of the two sets F and E, and we divide that by the probability of the event that's conditioned on. So we're conditioning on E, so E appears here in the denominator. But notice that E intersecting F is the same set as F intersecting E. So the probability of F intersecting E is just the same as the probability of E intersecting F, which is probability of E multiplied by probability of F. These cancel, so we get the result. X follows a normal distribution with mean 60 and standard deviation 5. We know that a normal distribution is meant to be symmetrical about the mean mu. We want a probability that X is less than or equal to 68. So all the values of X lie along this line here. We're interested in the probability that X is less than or equal to 68, which is somewhere over here. Well, so what we want is the probability that X is any value from minus infinity up to 68. So in theory, X runs from minus infinity to this value. And we know how to get that probability. That probability is got by getting the area above this colored line here. And of course we can't just look this up. This particular normal distribution we have to standardize to the normal distribution with mean 0 and standard deviation 1. So we want a value corresponding to 68. So here's our formula for getting the transformation. So we want to see how many standard deviations 68 is from 60. So we have to take x, which is 68, subtract the mean 60 to get the distance of this value from the mean, and divide by sigma to see how many standard deviations 68 is from the mean of 60. So we get 1.6. So our problem involves getting the probability that the z value, so all the z's lie along the horizontal line, runs from minus infinity to plus 1.6. So that's the area under the standard normal distribution, whose mean is 0, standard deviation is 1. So the probability that x is less than or equal to 68 for this particular normal distribution is equivalent to the probability that z is less than or equal to 1.6 for the standard normal distribution. The letter z is used for the standard normal distribution. Okay, so let's look up that value. So I've gone to Wikipedia, and you can see from the picture here that we have a standard normal distribution, but the shaded area runs from 0 to the value that we're interested in. Of course, we want to go from minus infinity to that value. But let's look at the area from 0 to the value. So the value that we are interested in is 1.60. So the first decimal place is 0.6, the second decimal place is 0, so we're going to get 0.43319 here. But we have to add 0.5 onto that, because the total area underneath the distribution is 1, so the area from minus infinity to 0 is a half, so we have to add a half onto this yellow region. So the yellow region could be this value here, okay, if the z value is 1.6, so we want 0.5 plus 0.4452. So as a reminder, half the distribution runs from minus infinity to 0. So that's 0.5. We add on 0.4452. So our final answer is going to be 0.9452. So that's the probability that x is less than or equal to 68. Next, we want the probability that x lies between 52 and 68. So we want the area under the curve between 52 and 68. Notice here that the distance of 60 to 68 is the same as the distance of 60 to 52. So we can use symmetry to answer this problem here. We've already gotten this area here. Okay, we saw from the table that it's 0.4452. So this area here is also 0.4452. Doubling 0.4452 gives us 0.8904. So that's the area in here from x equals 52 to x equals 68. The heights of a certain type of plant when ready to harvest are known to be normally distributed with a mean of mu. The diagrams show the expected distribution of the heights of the plants at harvest time without the use of hormones. So this curve here is the distribution of plants without the use of hormones. You can see the mean is mu, so it's a normal distribution centered at the mean mu. A company tests the effects of 3 different types of growth hormone on this type of plant. The 3 hormones were used on different large samples of the crop. After applying each hormone, it was found that the heights of the plants in the samples were still normally distributed at harvest time. Okay, so in diagram A, we have we want to show the expected distribution of the heights of the plants at harvest time. Well, this shows it without hormones, and we apply one of the 3 hormones, hormone A, which has the effect of increasing the height of all of the plants. So we call the height h. H is a random variable which is normally distributed with mean mu and some standard deviation that's not given in the question, but we'll call it sigma. Okay, so all the heights are along this horizontal axis here, and they're distributed about mu. But this first growth hormone increases the height. So basically, the mean height is greater now after the hormone has been applied. So it's mu plus some number. I don't know, let's give it a name. Let's call it D. Okay, but the idea is that the distribution is still normal, but now it has a greater mean. So the heights have all been increased, so it's like we're adding D onto all the heights. So if we pick a value here for our original distribution, we add D onto it to get the corresponding value that follows our new distribution. So here's our new distribution. Okay, so we could call this new distribution, well, it's normal, but now with a bigger mean. And it looks like the standard deviation hasn't changed. Okay, so this is an official answer to this problem. You can see that this curve has exactly the same width as our original curve. So sigma determines how wide our distribution is. So basically all we did was shift the distribution to the right. So you know, the heights of all the plants have increased, but they still follow the same distribution, exact same shape as before. Now let's look at a situation after hormone B has been applied to a large sample of our original plants. The effect of hormone B was to reduce the number of really small plants and the number of really tall plants. So the really small plants will be to the left end of this distribution. So all these values around here, you know, well, in theory it runs from minus infinity, but of course in practice we don't have negative values. You know, the smallest height would be 0. Smallest possible height would be 0, of course. But you know, all the really small heights are at the left end of this distribution. All the values along here, this left end of our horizontal axis. So the axis, horizontal axis, represents the heights, of course. So you know, so we want to reduce the proportion of plants along here, and also the proportion of really tall plants. So all these values at the right end of this axis, height axis. Okay, so all these values here are very high values for the height. Of course, the mean height is here. So before the hormone was applied, you know, this, if we want a proportion of plants, say, with heights running from the smallest possible height to, say, this value here, we would have to get this area. And similarly, if we wanted the proportion of plants at the extreme end, you know, the tallest plants, say, running from this high value to the highest possible value, we would have to get this area here. That's what we would do before the hormone was applied. But we want these areas to decrease. Okay, so we want smaller proportions at either end. So we want the tail of our curve to move down towards the horizontal axis. And that's exactly what happens when we apply the hormone. So now we get a much smaller proportion of small plants and a much smaller proportion of very large plants. So we just flatten the tails of the distribution, but the total area under the distribution does not change. So the total area must be 1, remember, okay? It's a probability distribution. You know, the proportion of plants of all heights is just 1. So, you know, if we flatten the tails, we'd have to increase the height of the curve. Okay, so that means that total area under our new curve would have to be the same as the total area under the old curve, representing the heights of plants before hormones were applied. So we want to keep the area under both curves equal to 1. Finally, we have hormone C, which has the effect of increasing the number of small plants and the number of tall plants. So all small plants are represented on the left end of our axis, and the tall plants are at the right end of the axis. Okay, so the proportion of small plants in the case of no hormone is given by the area under this curve. But after the hormone, we want to increase that proportion. Okay, so we want to have this. We want to increase to this here. So we have to widen this tail. Well, I should say fatten this tail, and the same goes at the other end. Initially, this area here would be the proportion of, say, all the tall plants running from this value up to the highest possible value. And we want to make that proportion even greater, so we have to fatten the tail. But of course, by fattening the tail, we have to compensate by decreasing the height of the curve. So we want our new curve to be a normal distribution with the same mean as before, centered at mu, symmetrical about mu. But we want the total area under it to equal the total area under the original curve, which is 1, of course. So the area under both curves must be 1. So if we fatten the tails, we have to compensate by decreasing the height. So the area under both curves is the same, namely equal to 1. Go Fast Airlines provides internal flights in Ireland, short-haul flights to Europe and long-haul flights to America and Asia. On long-haul flights, the company sells economy class, business class and executive class tickets. All passengers have a baggage allowance of 20 kilograms and must pay a cost per kilogram for any weight over the 20 kilogram allowance. Each month, the company carries out a survey amongst 1,000 passengers. Some of the results are shown here. So we see the gender, 479 male passengers, 521 female. So these two numbers must add up to 1,000, of course. Those who answered yes to the question, have they previously flown with Go Fast Airlines? And we have the number that answered no. Again, these two numbers must add up to 1,000, of course. 1,000 people are in the survey. We have the number that say they would fly again with that airline, and the number who say they won't. Again, these two numbers add up to 1,000. We have the mean and median passenger age. We have the mean and median spend on flight facilities. We have the number of people who said the flight was delayed, and the number who said the flight was not delayed, and also the number of people who say they don't know whether or not the flight was delayed. And we've passenger satisfaction numbers here. And again, all of these numbers must add up to 1,000. Go Fast Airlines used a stratified random sample to conduct the survey. So that means that we take a large population of people who used Go Fast Airlines. Okay, that population might consist of, say, 1 million people. And we divide the population into different subgroups which have common characteristics. So for example, we could divide our population into these 4 subgroups. Okay, so each group have a common characteristic that we saw at the start of this question: different types of flights and different classes of flight. Random samples are drawn from each subgroup according to their proportion of the population. As an aside, let's look at a possible sample of size 1,000. So let's imagine that for the month of May, 100,000 people used this particular airline. And let's suppose that the population is broken down by these particular strata. 1/3 of the people use short haul, 1/3 of them use long haul economy, 1/4 use long haul business, and 1/12 use long haul executive. So if we want a representative sample of size 1,000, we would have to take a simple random sample of size 333 from the stratum representing short haul passengers. Similarly, we would have to take a simple random sample of size 333 from this subgroup or stratum representing all long haul economy passengers. Of course, we have rounded here. The exact value would be 333 1/3 for each of these. But just after rounding, that's roughly what we will have. And here we would have to take 1/4 of 1,000 or 250. And finally, what's left over? Well, everything is supposed to add up to 1,000. So we could say take 84 here. So, these are approximate. Well, they're very good approximations to our actual proportions here. Next, we get the probability that a passenger selected at random from this sample had their flight delayed. Okay, if we go back to the table, the number that said their flight was delayed was 231, so that's out of 1,000 people. Now 21 people said that their flight was not delayed, so we could discard this 21 people who were unsure and just take those people who were sure of whether or not their flight was delayed. So if we take 21 from 1,000, we get 979. So another way we could calculate this is to put the number of people who were sure their flight was delayed, that's 231, over the total number of people who were sure whether or not their flight was delayed. So this second fraction here may give us a better idea of the proportion of people whose flight was delayed. Next, we want the probability that passengers was not satisfied with this overall service. So we just get the number of people who are not satisfied with the service. That's 238 over the total number in the sample, which is 1,000. So we get it from this table here. Perhaps to get a better estimate of that proportion, we should disregard the people who weren't sure about their satisfaction level, whatever that means. Okay, so that's 98, so we take 98 from 1,000, so we get 902 people who were sure about whether or not they were satisfied with the service. An employee suggests that the probability of selecting a passenger whose flight was delayed and who was not satisfied with the overall service should be equal to the product of the two probabilities in part 1. So let's consider the two events that the probabilities refer to. One event is that the passenger is not satisfied. Let's call that event N, N for not satisfied. The other event, D, is that the flight was delayed. Now let's imagine that both of these events are independent. So let's look at the probability that a customer is not satisfied given that the flight was delayed. Well, we can use our conditional probability formula here. So we know what to do. We just get the probability of the intersection of these two events. That's the probability of a passenger not being satisfied and the flight being delayed. And we divide by the probability of the event that's conditioned on. So D is the event that's conditioned on, and that appears in the denominator. Okay, so that's just a formula for conditional probability. Now, if N and D are independent events, well, the probability of N given D is just equal to the probability of N. So now we can put our conditional probability formula equal to the probability of N, and as a consequence of that, we can see the probability of a passenger not being satisfied and the flight being delayed is the product of the probabilities. It's the probability of not being satisfied times the probability of the flight being delayed. So we saw this before. So basically we would just multiply the probabilities. But of course, you know, we are not surprised to understand that N and D are not independent events. You know, we would expect the probability of a passenger not being satisfied to depend on whether or not the flight is delayed. If the flight is delayed, this probability goes up. If the flight is not delayed, you know, we would expect the probability of N to go down. Okay, so D bar stands for the event that the flight is not delayed. So this is what we would expect to be true. If the events were independent, well, you know, these things would be equal. Okay, so the answer to the question is that we do not multiply the probabilities because N and D are dependent events. The probability that a passenger is not satisfied depends on whether or not the flight is delayed. Now, as an aside, let's look in more detail at the situation where N and D are actually independent, and we will show that in that case this probability will equal this probability. Okay, it won't be greater than it, it'll actually equal it as we'd expect. Both probabilities are the same, regardless of whether the flight is delayed or not. Okay, so to do that, we can look at the probability of a customer not being satisfied. That's not conditioned on anything. And let's see how that comes about. Well, there are two possibilities for a passenger not being satisfied. Either the passenger is not satisfied and the flight is delayed, or the passenger is not satisfied and the flight is not delayed. Okay, so it's one of these events, one or the other, so we add the probabilities. So next we use a conditional probability formula. So I just rearranged it here to get the probability of n intersecting d. So anyway, there's a reminder of the conditional probability formula. So we just cross multiply to get this result here, and we have a very similar result for the probability of n intersecting d bar. But we are saying that n and d are independent, so we can replace probability of n given d with probability of n. So n doesn't depend on d. Now we can move this term over to the left hand side and factorize out p of n, and this is what we get. Now the probability of a flight not being delayed, p of d bar, is just the same as 1 minus p of d. It's 1 minus the probability that the flight is delayed. So this thing here is just p of d bar. So we end up showing that in the situation where n and d are independent, that p of n is equal to p of n given d bar. So that's the situation where n and d are independent. These two probabilities are equal, and as we saw before, if n and d are not independent, we would expect this probability to be greater than this probability. Okay, if a flight is delayed, the probability of a customer not being satisfied is greater than the situation where the flight is not delayed. By the way, I should say that writing p of n in this manner here was something that we saw in a previous video. It's referred to as the theorem of total probability. Here we have three possibilities for the distribution of the weights of passenger baggage. So, along the horizontal line we have the weight of passenger baggage. 20 kilograms is the cutoff value for a charge being applied to baggage. Okay, so for example, if the distribution looks like what's shown here, we might be interested in the proportion of baggage that weighs less than 20 kilograms. Okay, so the weight is along the horizontal line here. So for baggage weighing less than 20 kilograms, that weight ranges from a minimum value, which would be 0 in this case, not actually minus infinity, to a weight of 20. So all those weights would be indicated by this red line here. So the proportion of baggage that has all these weights is given by the area under the probability distribution. And you can see in this case that it looks like the area is a half. If we are interested in the proportion of baggage that weighs more than 20 kilograms, we consider the area under this bit here. And this looks like a half also. So it looks like as if we have as much baggage weighing more than 20 kilograms than weighs less than 20 kilograms. Now that doesn't seem likely, since we have a charge being applied to baggage that weighs more than 20 kilograms. So we would expect a relatively small amount of baggage to weigh more than 20 kilograms, and that's reflected in this distribution here. Okay, so the proportion of baggage that weighs more than 20 kilograms is given by this area here, which is small compared to the proportion of baggage that weighs less than 20 kilograms, which is given by this area here. So it certainly looks like this is the most plausible graph. This one here makes no sense, because it's saying that a relatively small amount of baggage weighs less than 20 kilograms, and most of the baggage weighs more than 20 kilograms. This big area here, that doesn't make any sense. Next, we will look at a sketch of the possible distribution of the ages of the passengers based on the data in the survey. Alright, so here we have the section on passenger age. Notice that the mean age 42 is greater than the median age of 31. Now, we saw previously that the median of a distribution is the value that cuts the area of the curve into two equal parts. So the area to the left at 31 must be a half, and the area to the right is also a half. The total area under any probability distribution is 1. So what a median of 31 tells us is that half the people have ages below the 31 and the other half have ages greater than 31. Now we saw previously that the mean of a distribution is the balance point of it. So if you can imagine that we have this curve balanced on this horizontal line here. Okay, so we have like something like a seesaw balance at this point here. Well, even though we may have more area to the left than we have to the right, you know, if the balance point, if the mean is greater than the median, you can see clearly we've more area to the left, more than half. We still get balancing here because, you know, we have this longer tail which has more leverage. So we could have greater weight on the left hand side or greater area on the left hand side, but that makes no difference because we still get the thing to balance if you know, we have a lot of material that's, or some material that's a long way from the balance point. So we could think of balancing this weight on our seesaw, if you like. So the mean in this example is 42. So when that happens, our curve is skewed to the right. So the tail of the curve skews to the right. So the height of the curve, the peak of the curve, is to the left, if you like. We have a fatter tail here at the left. We have a thinner tail at the right. The company repeatedly asserts that 70% of their customers are satisfied with their overall service. Use an hypothesis test at the 5% level of significance to decide whether there is sufficient evidence to conclude that their claim is valid in May. So, the null hypothesis here is that the population proportion of satisfied customers is 70% or 0.7. So we're looking at the population now, which could consist of a huge number of people, and it's the population of travelers or customers for the month of May. Okay, so this is our null hypothesis. So how can we test this claim? Well, the alternative hypothesis, of course, is that P is not equal to 0.7. So we're going to use our sample, which at size 1000, to test this claim. Well, let's get the sample proportion of satisfied customers. So if you go to your table, you'll see that 664 customers out of 1000 were satisfied. So our estimate for P hat is 0.664. Now if the claim is true that the population proportion is indeed 0.7, well, we would expect our P hat to be close to 0.7. Now we saw in a previous video that if we repeatedly took samples of size 1000 and calculated P hat, that is the proportion of satisfied customers, out of each sample, those P hats would follow an approximately normal distribution whose mean is equal to the population mean P. Now normally we don't know what P is, and you could say we don't know what it is here either, but we're hypothesizing that P is 0.7, so we're assuming that P is equal to 0.7. We also saw previously that 95% or approximately 95% of all the sample proportions, that is all these values along this red line, lie within a 1 over root n of P, where n is the sample size. Now in a previous video we saw a more accurate value for 1 over root n that we will use later on in this video. So for now I will use a simpler form. Here you can see I've calculated P minus 1 over root n and P plus 1 over root n. So if the null hypothesis is true, we would expect our particular value for P hat to lie along this red line. Let's see where it is. Okay, well 0.664 clearly is outside of this region. So that means we reject the null hypothesis and conclude that the population proportion is not 0.7. See, we've got such a, well, it's actually a small value of P hat that maybe the population proportion is less than 0.7, for example. Okay, it's still possible that the population proportion is equal to 0.7, and we just happen to pick one of the 5% of samples whose values lie outside this region, okay? So 95% of them lie between 0.6684 and 0.7316, and the remaining 5% are either less than 0.6684 or greater than 0.7316. Okay, it could still be true that the null hypothesis is true. But anyway, that's not what we do. We reject at the 5% level of significance. Okay, so we just conclude that we reject the null hypothesis. Of course, we could have also done this without calculating p minus 1 over root n and p plus 1 over root n. We could have simply got the distance of our p hat 2.7 and compare it to the margin of error 1 over root n. Okay, so we could have got this distance here just by subtraction, of course, 0.7 minus 0.664, and we would have seen that that's greater than 1 over root n, which is just this distance here. Okay, 1 over root n is 0.0316. Okay, the distance between p and p hat is p minus p hat, and we just take the magnitude of that just to make it positive. You know, it's quite possible that p hat could have been bigger than p, and in that case p minus p hat would be negative, but we want the distance, so we want to make it positive, so we take the magnitude. And the distance of this point here to p is, of course, the margin of error 1 over root n. So anyway, if our p hat lies in the blue region, that is less than 0.6684 or greater than 0.7316, we reject the null hypothesis. Now let's repeat this problem with our more accurate formula for the margin of error. So this is the more accurate formula for the 95% margin of error for a population proportion. It involves p, which is the population proportion. Now normally we don't know what p is, and if we're going to use this formula, we use p hat in place of p. Not as accurate, but better than using the formula 1 over root n nonetheless. However, we are hypothesizing that p is 0.7, so we're assuming that this is true. So 95% margin of error is got by plugging 0.7 in for p, and if we calculate this thing we get 0.029. So under the null hypothesis, all the sample proportions, that is all the p hats, follow a normal distribution with mean equal to the population proportion p. So it also follows from what we've done previously that 95% of all those p hats lie within this margin of error of p. So this value here is just 0.7 minus the margin of error, which is 0.029, and of course this value up here is just 0.7 plus the margin of error 0.029. Now, as an aside, we saw previously that our simpler formula for the margin of error is actually the maximum value of our more accurate formula. Okay, we proved that in the previous video. So the value that we get for this more accurate value is always going to be less than 1 over root n. Anyway, let's see if we can test this hypothesis. So let's look at p hat. It's 0.664. Well, that's here. You can see it's in the rejection region. It's in the blue region. Okay, to be in the rejection region has to be either less than 0.671 or greater than 0.729. As I said before, we could also have found that out by getting the distance of our p hat to p. So this is p minus p hat. Well, we get the magnitude of it in case it comes out to be negative. And we compare that to our margin of error, which is this distance here. Well, you can see that that's 0.029. So anyway, if you do this calculation, you get 0.036 for that distance between p and p hat, and you can see that that's greater than 0.029, so we reject the null hypothesis. if we reject the null hypothesis when using this value for the margin of error, well, we're obviously going to reject it when we use this smaller value over here for the margin of error. A manager of the airline says if we survey 2,000 passengers from June on, we will halve the margin of error in our surveys. Okay, so for a sample of size n, we know that the margin of error is 1 over root n. So if n is 2,000, the margin of error is 1 over root 2,000. We want to see if that is half of our previous margin of error, where the sample size was 1,000. Well, half of 1 over root 1,000 is not actually equal to 1 over root 2,000. As a matter of fact, if we wanted to half the margin of error, we would have to survey 4,000 passengers. If you calculate the margin of error for a sample of size 4,000, we would have 1 over root 4,000, which is actually half of 1 over root 1,000. So we need to have a sample size that's 4 times greater if we want to half our margin of error. Here we have a table showing the responses of in-flight spend for 10 passengers, and we have the ages of each of those 10 passengers. Now we can see from the scatter plot that as age increases, in-flight spend appears to increase. Now we want the strength of the linear relationship between the variables spend and age, and to do that we calculate a correlation coefficient between the two variables. So we're going to use this particular calculator, and we start by using the menu key here, and we go to Stat, which is button number 2, and we can feed in the coordinates of our points. Okay, so we tap in 46, right arrow, or well, return 29. So I just put in all the age values or x values. Just push return each time. Okay, so after doing that, we just move to the next column and type in our y values. So we have 30, 15, 20, 0, and so on. Okay, we can actually graph our points. Click on graph here. Now we want graph 1 because that gives us a line. Well, I'm not actually sure what graph 2 and 3 do, but I just press on graph 1, and if we press calculate, now here we have this symbol x, so we want linear regression. That means we want a line. Okay, so it's just x to the power of 1. X squared will give us a quadratic curve that fits the points. We don't want that, so we just press x here, and we're interested in just a correlation coefficient, which is r. R is a number between -1 and +1. Okay, so we saw this before. If r is -1, well, we have a perfect linear relationship. All the points lie in a straight line, but our line has negative slope, and it doesn't matter actually what the slope is. As long as the slope is negative, we'll get a value of r which is -1. At the other extreme, we have a situation where r is +1. In that case, we have a perfect positive linear relationship. So all the points lie on a straight line which has positive slope. And again, it doesn't matter what the slope of the line is. As long as that line has positive slope, r will equal +1. Now, in between -1 and +1, we have a range of possibilities. In the middle, where r is 0, we have no linear relationship. So in that case, our points don't follow any obvious linear relationship whatsoever. That's the situation where r is 0. So here, r is -1. Over here, r is +1. So the value that we got, which was r equals 0.88, indicates a fairly strong positive linear relationship. So you can see our line has a positive slope, and since r is close to 1, our points are quite close to a straight line. Now with this calculator, actually you can see the equation of our line of best fit. So here's the line. Its equation is ax plus b. So a is the slope of the line, it's the coefficient of x. You can see it's 0.67 roughly. B is the intercept, the y-intercept of the line. So this line cuts the vertical axis at roughly minus 4.5. So basically, a correlation coefficient that's close to +1 tells us that as age increases, spend increases linearly. It's quite a strong linear relationship. So older passengers tend to spend more